Okay, start with this question, people. Okay, so let me start by giving you kind of hint on how to write the wave equation. So this is the snapshot picture at t equal to 0. So write the equation of y versus x at t equal to 0. Okay, so from that we'll get the rest of the thing. So from this above diagram you can see that okay, that is this part of the straight line y is equal to mx plus c. You can see its slope is 1. Okay, but only thing is the slope here, y is in millimeters and x is in centimeters. So that slope which is there is 1 millimeter per centimeter. That's one important thing to understand over here. Okay. Okay, whereas this part you can see the slope is minus half. Okay, and the y-intercept is, so it is minus x by 2 plus 2 for x being, let's say, greater than equal to 0, less than equal to 4. Again, x is in centimeters, so the slope in this part is minus half millimeter per centimeter. Okay, so now from this we can understand that at some later time the pulse is, let's say, over here, right? So suppose this is the pulse at some time t, then what has happened is that the peak of the pulse would have got displaced by how much? It would have got displaced by 20t. Okay, so the displacement of the pulse would be equal to vt, like this. So what we do in the equation of the pulse is we replace x with, so we replace x with x minus vt. Okay, so this will become x minus 20t plus 2, when x minus 20t is between minus 2 and 0, and it will become minus half times x minus 20t plus 2, when x minus 20t is between 0 and 4. Okay. So again here the coefficient of x, so you can see the equation is of this type: y is equal to kx minus omega t plus 2, and it is minus half of kx minus omega t plus 2. So this type where k is equal to 1 millimeter per centimeter. Okay. Or we can even think of it like this, that this is k is actually 1 centimeter inverse. There is like a e over here, that e is equal to 1 millimeter, and omega is 20-second inverse. That is for this one. And here that minus half is actually minus half millimeters. So this is the form of the equation. Okay. So anyway, as far as the equation of the wave is concerned, our final answer will be this one. But you have to just understand the dimensionality over here also. So the dimensionality of this equation is such that x is in centimeters, t is in seconds, and y is in millimeters. So this is the answer to the first part, the equation of the wave. Hope this is clear to all of you people. No, this is a traveling pulse, so it's not a periodic wave. Yeah, it can be written as a very, very complex series of sine and cos waves added, but that is Fourier transformation and it's not in our syllabus. So that is something far more complex. Okay, so here we have to understand that it's a traveling pulse. So it's a non-periodic function. And plus in this case, it's a triangular traveling pulse. Yeah, so Ganesh and Somadip, you mostly got it correct. Okay. Okay, so now we will talk about the second part. So in the second part, when you're putting T as this thing, how much is it now? 1 second. So if you look at the snapshot picture at T equal to 1 second, the peak of the pulse would have gone to 20 centimeter position. Okay. So T equal to 1 second. So we can use this kind of relation over there, that y is equal to some function of kx minus omega t. We have written like that over here. where that function was of that type. It was, in this particular case, it was like this: kx minus omega t plus 2, when kx minus omega t is in between minus 2 and 0, and it is minus half of kx minus omega t plus 2 when kx minus omega t is between 0 and 4. Okay, like this. So particle velocity is del y by del t, which from the above equation you can see is minus of omega f prime kx minus omega t. But rather than calculate all this, we can use a trick that del y by del x is k times f prime kx minus omega t. So you can see that at t equal to t, x equal to x, the particle velocity is nothing but minus omega by k times del y by del x. Okay, and here you could see that omega was 20 second inverse and k was 1 centimeter inverse. Okay, but remember y was in millimeters, like this. So we can make use of this, where del y by del x at any point is the slope of the tangent at this snapshot picture. Okay, so now if we are looking at the point x equal to 22 centimeters, the slope at this point right now is how much? It is minus half, but remember it is in millimeters per centimeter. So the slope is minus half into 10 raised power minus 1. So it's actually minus 1 by 20. Okay, so you can see over here we will substitute that. So particle velocity at x equal to 22 centimeters, t equal to 1 second, will become minus of 20, okay, divided by 1, but that will become in centimeters per second, okay, into slope at x equal to 22, t equal to 1 second. So it will become minus 20 into that slope was minus 1 by 20. So it will be plus 1 centimeter per second. So that is the particle velocity at x equal to 22 centimeters, precisely at t equal to 1 second. Okay. So this particle actually has an upward velocity of that much at this instant. Now you can also do it by this method, by this. So you can also do it like this, that okay, so that you can see is, if you were to do this partial differentiation, it would be minus omega and it would be okay. But in this, you have to understand one thing here, that in this equation, this is minus 1 millimeter per centimeter into omega, and this is half millimeter per centimeter into omega. Sorry, that centimeter will cancel out. So let's understand the dimensionality of this equation again. So if this quantity kx minus omega t is dimensionless, then the quantity y is in millimeters. So there's a constant of 1 millimeter here, and this minus half is in millimeters. Okay. So this will actually become okay. So you can see that x equal to now kx minus omega t is actually k's value was 1, so it is x minus 20t. It's like this. Okay, so x equal to 20 to t equal to 1 second, it is equal to 2. Okay, so the particle velocity should come in this category. It should be plus 1 by 2 omega in millimeters per second. So it is okay. So that's the same thing as plus 1 centimeter per second. So that is a relationship between these two methods. Ganesh, we cannot say directly V is equal to omega, no? Understood, because of that. because there is a factor outside also, na here. And Shushruth, you understood how to do by time derivative? This part which I've written over here. I'll just enlarge it for you a little bit. If you want to do by the time derivative method, then this is how we'll have to express it. Okay. This is coming from this equation. So from this only we are getting the time derivative. I guess. So when you understand this equation, no, you have to understand that here there is a 1, and that is 1 millimeter, and this is 2 millimeters because y is in millimeter, and this minus half is in millimeters, and this 2 is in millimeters. Yeah, so understood now. So that's why in a problem like this, the units thing can get a little confusing. So if you're doing the particle velocity, it's easier to work it out by just using the relationship between slope of the tangent at that point and this. Okay, let me move on to the next question. Okay, so this is again a snapshot picture of a sinusoidal wave this time at time t equal to 0. And from the information given in the graph, okay, we have to determine this thing, these various parameters. Okay. Nee, Ganesh, check your wavelength once more. So I'll just give you a hint over here. First, compare this graph, the graph of this type. So this is a graph of 1 plus sine x. Okay. So now, if you look at a more general graph, this type of graph, if you look at. Okay. So we can see that this will be one full wavelength. Where k is equal to 2 pi by lambda. Okay. Now we can also see that this point here, so let's understand these two values. So this is lambda by 6. So this becomes how much? This becomes lambda by 2 minus lambda by 6. becomes lambda by 3. Okay. So therefore, transformation wise, that graph that we have drawn, starting from this point, so the whole graph is shifted back accordingly. So the graph is starting from this point. So the whole graph is shifted back by lambda by 3. Okay. So if this were to be a stationary graph, this would be the snapshot pictures graph would be 1 plus sine k into to write it like this. Okay. Oh, my mistake. This is not correct. This is lambda by 12. So this point will be different. It's pi by 6. Sorry, that point is 30 degrees now. So it is, yeah, pi by 6. So lambda by 12. Okay. So this point here will become lambda minus lambda by 12. So it will become 11 lambda by 12. Okay, so this is, it's like this actually. Okay. So this is the snapshot picture at t equal to 0. So you can also see that this point here, which was the above graph, it was 0.6 centimeters. Now this distance from here to here, this distance is equal to, in terms of lambda, it is how much? It is 3 lambda by 4 minus 11 lambda by 6. Sorry, 11 lambda by 12. Or if you think more simply, you're just basically going from this point in this graph to this point. So you're going 1/12 plus 1/4. Or in other words, in the standard sine graph, you're going from this point where theta, suppose we said this is theta. So theta is 5 pi by 6 to this point where theta is 3 pi by 2. So the delta theta between these two terms is nothing but pi by 6 plus pi by 4. So that is how much now? 2 plus 3, 5 pi by 12. So your delta x between these two terms will, in terms of lambda, think in terms of that, is going to become 5 lambda by 24. It's basically lambda by 4 plus lambda by 12. Okay, so that is equal to 0.6 centimeters. So my lambda is how much? 24 into 0.6 divided by 5. Okay, so that will become how much? Twenty-four into 0.6 is 14.4 divided by 5. So lambda should be 2.88 centimeters. Okay. So now coming back here, we've also got the equation for this. The snapshot pictures equation, y at t equal to 0 is 4 into 1 plus sine kx minus 5 pi by 6. Okay. Where k is 2 pi by lambda, and lambda we just saw is 2.88 centimeters. Okay. So therefore, so lambda is this, and of course frequency will become v by lambda. So the frequency will become 5 centimeters per second divided by 2.88 centimeters. So like we can write it as 125 by 72 hertz. Something like this. Okay. Ganesh, you're getting a different wavelength. But see, at this point, x equal to 0 corresponds to a phase of how much? It corresponds to a phase of 5 pi by 6. And x equal to 0.6 corresponds to a phase of 3 pi by 2. So delta x equal to 0.6 corresponds to a phase difference of this much, no? This should be the direct way of understanding it. Wait a second. Wrong here. Oh, wait. Sorry, sir. My mistake. This is pi by 2, no? Not pi by 4. This is pi by 6. Okay. And this is pi by 2. So this is becoming how much? 2 pi by 3, sorry. So this delta x is not this much. It is lambda by 3. Okay. As you can see here also. Lambda by 3. So lambda by 3 is equal to 0.6. My mistake. Okay. So you have to redo the calculation a little bit. So so lambda will come out to be 1.8 centimeters. Okay. Okay, so this is our frequency. So now our wave equation, so lambda should be 1.8 centimeters. Yeah, we can also write it as a sine square graph, but then there'll be some modifications. Okay, so that will become equivalent to this. Now equation of the wave में क्या करेंगे? This has to be converted. So y as a function of x and t will become 4 into 1 plus sine kx minus omega t minus 5 pi by 6. Okay, such that now okay, so this becomes okay, and omega becomes sorry, k is in radians per centimeter. This is in radians per second. Okay. So this is our second part's answer. And then we can get particle velocity and all quite easily. That's not going to be very challenging after this. Now there's also another way we can approach this question, which is something you have been trying, I think, Somoru, that we can write it as a sine square or a cos square type of function. Oh, sorry, the amplitude is 2, my mistake. That's correct. This is 2, not 4. Okay. 2 millimeters. Okay, so I mean, I have given a very lengthy way of solving this, but let me just explain how you can do this very fast. I have explained to you from the fundamentals, but at the exam level, how you should do this is something like this. You were given this graph. Right. Whatever I mean. Okay. So this is okay. This point was given to us as 0.6. It's traveling with 5 centimeters per second, and it's given as a sinusoidal wave. Okay. So now you can see that this is a sinusoidal wave with a mean position. Matlab, you have to compare it with this kind of standard sinusoidal wave. So this is E into 1 plus sine theta, where theta is omega t minus kx plus phi, or kx minus omega t plus phi, whatever. Okay. So now when you look at this, you can see that this point corresponds to a phase of 5 pi by 6, because in a standard sine graph, you know that this is 5 pi by 6, and this point corresponds to 3 pi by 2. Okay, so now between these 2 points, you directly understand the phase difference is this much. It's 3 pi by 2 minus 5 pi by 6. Okay, or it is just the sum of these 2 phases, this plus this. So that is pi by 6 plus pi by 2. So either way you do it, and you see that this comes out to be pi by 3. Sorry, 2 pi by 3, this phase difference. So the phase difference is 2 pi by 3. That means delta x is lambda by 3. Okay, so that lambda by 3 is 0.6. So straight away from there you get lambda is 1.8 centimeters, and v is equal to f lambda. So from that you get frequency is 25 by 9 hertz. So from this now you know k, from this now you know omega. So all this is done. Okay. Now the only thing remaining is the initial phase, and that also you can see this point is 5 pi by 6 now. So had we had this one, this would have been y is equal to e into 1 plus sine kx. So this one is becoming e into 1 plus sine kx minus 5 pi by 6. Okay, so this is a snapshot picture at t equal to 0 as a function of x. So now y as a function of xt, just replace k into x. In this you have to replace x with x minus vt, or in other words you have to replace kx with kx minus omega t. So the wave equation becomes e into sine, sorry, e into 1 plus sine kx minus omega t minus 5 pi by 6. This becomes our wave equation, where you can see from comparison the amplitude, as you correctly pointed out, is 2 millimeters. Okay. And k and omega you're getting from this. K is 2 pi by lambda, omega is 2 pi f. So this is the way of doing the equation. Okay. And then you know the standard formula for particle velocity and all that. So that's not tricky. Okay. So just complete the analysis of this and take a 5-10 minute break, and we'll continue with some more problems, gradually moving towards superposition next after this. All right, so a final answer for the wave equation was this. Yes, this was our wave equation. Okay, so students, let's pick it up again from here. Now, before we move on to the next question, we will just also understand how we could have done this question using the sine square function. Okay. So first of all, this thing that we have got, you can always convert it to a sine square function. By doing this, write this as, first you convert this to a cos. Okay. Be this. Okay. And then write this as a into, write your cos as 2 cos square minus 1. Okay. So this way you can convert it to a cos square or a sine square function. So this will become 4 millimeters into cos square, let's say k prime x minus omega prime t minus pi by 6. Okay. Where k prime is k by 2. So over there we had got k as 10 pi by 9. So here it will become 5 pi by 9. And omega prime is omega by 2. So it becomes 25 pi by 9 radians per second. Okay. And you can always convert the cos square also to sine square by adding pi by 2 or whatever. That's fine. So that's one way of expressing it. Or the other is you could have started with the sine square function only. Sine square or cos square function, whichever. And you would have come to this. Okay. So this is the same thing as sine square k prime x minus omega prime t, and again we'll have to make this pi by 3 because we'll use the function that cos square theta is sine square theta minus pi by 2 or plus pi by 2 or whatever. All right, so many different ways of expressing it. Now we could have also done this directly from the graph. So what we would have done is we would have compared our given graph to a standard sine square graph. So a standard sine square graph like this. So now this point, okay, will correspond to sine square becoming how much? 3/4. Okay, or sine becoming root 3/2. I mean plus minus root 3/2. So here it's okay. So this would be lambda by 3. Okay. But remember here the k that we've written, I mean, is that k prime term actually. So that k prime is pi by lambda. Okay. So this graph which is starting from this point, our original graph which was starting from this point, okay. So this would be a graph at t equal to 0 of the type 4 sine square ex plus some phase difference. Okay. So first of all, that phase difference you can understand. This corresponds to a phase point of how much? So sine square has to be 3/4. Okay. So sine has to be root 3/2. So root 3/2 in the sine inverse of root 3/2 in the second quadrant is how much? It is 120. So 120 is 2 pi by 3. Okay. So this can be written here, this phase constant phi naught can be written as minus 2 pi by 3. But because it's the sine square, that's the same thing as plus pi by 3. Because this function has a period of pi. So minus 2 pi by 3 is the same thing as plus pi by 3. So that's where this comes in. Okay. And now as far as your k prime is concerned, so that will come from this. The phase at this point is this point's phase now. Is 2 pi by 3. And the phase at this point is pi. So this phase difference delta phi is equivalent to pi by 3, which will be equivalent to lambda by 3. So lambda will again be equivalent to, I mean, this is equivalent to 0.6. So your lambda will again come 1.8 centimeters. Okay. Which means your frequency by V by lambda will come out to be the same, 25 by 9 hertz. But this time the difference is that when you convert this to the function, we like this sine square k prime x minus omega prime t plus phi naught. So your k prime will become now pi by lambda because the period of the sine square function is pi. the fundamental period. And similarly, your omega prime will be equal to pi f. Okay. And phi naught will be, we can take it as pi by 3 or minus 2 pi by 3. It's one the same thing. So you can see that this function is the same as what we had got by mathematically manipulating the earlier one. But square किया ना बेटा? Oh, अच्छा, sorry. There I understood. Sorry. This will not be plus pi by 2. This we can write as minus pi by 2. Anyway, but ultimately it will come out to be the same thing, because cos is an even function, no? So cos of theta minus pi by 2 is cos pi by 2 minus theta, which is sine theta. So you can take that as minus pi by 2 instead. So instead of taking the plus pi by 2 over there, you can just take a minus pi by 2 and solve it similarly. But anyway, this is the method of converting it into a sine square function. Is it clear, Ganesh? Okay. So you can always, matlab, there might be some, but you know what will happen ultimately? इसको minus pi by 2 लेके किया तो it will come as that minus 2 pi by 3, and from that minus 2 pi by 3 is the same thing as uh, plus pi by 3, and like that. So ultimately the phase will come out to be the same. So it's the same as what you're getting from the graph method. Okay, so that's another approach of doing this question. Okay, now let us move on to some superposition based type of questions. Okay, now the next example is like this, that we have y1 is equal to, let us say, 10 sine pi by 4x minus 100 pi t. Okay, and we have y2 as, say, 20 cos of pi by 2x minus 50 pi t, where in both the equations x is in centimeters and t is in seconds. Okay, so if y1 and y2 superimpose, okay, then find Okay, try this out, people. Okay, that's correct, Ganesh. You can leave the answer in terms of pi by 8. So the E part's answer, you can see that with this. Okay. Okay, and you can always calculate sine pi by 8 as, okay, so Oh, my mistake. This here should be sine, no? Cos pi by 2 minus, so this will become sine. Oh, this is directly pi by 8, is it? Now, similarly, this term will also have just a pi by 8 here. In meters per second. So this becomes your second part's answer. I mean, particle displacement and particle velocity at x equal to 1 centimeter, t equal to 2.5 milliseconds. Now about the maxima, so you can see y as a function of time, I mean as a function of x at t equal to 2.5 milliseconds, that will become 10 sine. Oh, people, just a minute. I've understood. I made a mistake here actually. This should not be 50 pi. Because they are flowing in the same medium, na? So omega by k should be same. So this should be 200 pi. That is why we are getting some odd terms. This term here should be 200 pi. Okay, just make a correction. Because that's not possible. Now omega by k has to be same for both of them. So if this is having k double compared to this, you also have to have omega double compared to this. Otherwise, it's not logically possible. Understanding the point now? So just make a correction here. So that is why actually this question is much easier than this. It's not so complicated. So if this term is 0 now, this term also has to come 0. Okay. So y will just come as 20 and particle velocity will just come as minus 10 pi. Okay, and this minus 10 pi is coming in meters per second, assuming that this y is in centimeters, which I think I would have written earlier, right? Okay, so please make this correction, people. So this term has to be pi by 2. Okay. And rather than write it like this, we will now just write this like this. This is 2 sine theta plus 20 cos 2 theta, where theta is pi by 4x minus pi by 4. Okay. So we just have to find the maxima of this, which is not such a big deal. So इसका maxima निकालना है. So just do that dy by d theta and put it equal to 0 and all that. So ये जो भी वैल्यू आएगा ना, this will be the maximum. Okay. Okay, so first of all, people, hope you understood that earlier thing, na, it was why this is not possible, you know, that this should be 50 pi, because the two waves y1 and y2 are supposed to superimpose, so they are in the same medium. So if they are superimposing, they must be flowing through the same medium. Okay, so wave speed, which is omega by k, should be common for both of them. Oh, sorry, this one is minus 10, and this one will become how much? At 3 pi by 2, sine will be minus 10 and cos will be, so this one is minus 10. Okay, this will become minus 30, right? So your graph will be, that this is a number that will be, beyond 20. So it's starting from 20, it goes up to a maxima. Then pi by 2, it comes to a local minima of -10. Then again it goes to the local maxima, be the same as this value. But then it comes to a lower value of local minima, which is -30, yeah, at 3 pi by 2. And then it goes like this. So that is your y versus theta. And remember that theta is actually how much it is, pi by 4x minus pi by 4. So anyhow, this is how we'll analyze the maximum, minima, etc. All right, people, hope this is clear. Okay. So we'll just conclude with one more final question. Okay. So this string here is having a linear mass density of 2.5 gram per centimeter, and this here is having a linear density of 0.9 gram per centimeter. So if we have an incident wave, okay, so this has amplitude, let's say 2.4 millimeters, lambda equal to 12 centimeters, and frequency equal to 100 hertz. So find amplitude, frequency, and wavelength of the transmitted wave and the reflected wave from the junction. Okay, this over here is the junction. So we've discussed many questions like this, but just as a recap and revision, let's understand this. So this time the string on the other side is lighter. So we'll have to treat the boundary as a soft reflection point. Okay, so if you write this thing equation, power conservation equation, so half square root of t mu 1 omega square a naught square is equal to half square root of t mu 1 omega square into a reflected square plus half square root t mu 2 into omega square into a transmitted square. So you'll get a naught square is equal to a reflected square plus square root of mu 2 by mu 1 a transmitted square. So in this case, that will come out to be 2.4 square is equal to a reflected square plus ये कितना आ जाएगा 3 by 5 a transmitted square. So that's your first equation. Okay. And this time if you write a continuity equation at the junction, so if you take junction as x equal to 0, then y at x tending to 0 minus is going to be a naught sine omega t plus a reflected sine omega t. They'll add in phase, and that should be equal to a transmitted sine omega t, okay, which is y at x tending to 0 plus. So 2.4 should be equal to a transmitted minus a reflected. So that is your second equation. So solving these two equations, you will get a transmitted and a reflected. And about the wavelength and this thing, you can see that frequency of both will be the same. So the transmitted wave will have frequency same as the incident wave, so 100 hertz. But because your wave speed will become 5 by 3 times the incident wave speed, so lambda will also become 5 by 3 times lambda of incident. Okay, so lambda of incident was 12, so lambda of the transmitted wave will become 5 by 3 times 12, so that's 20 centimeters. Okay, whereas for the reflected wave the frequency is the same and the wavelength will be the same as the incident wave, so that is 12 centimeters. Okay, and now all you have to do is solve these two equations. So something like this, you can take E reflected as E transmitted minus 2.4, but anyway, that is whole square. Okay. So you can just verify my answer, but this is the method of solving it. No, so Ganesh, see, what we are doing is, if we write the incident wave as a naught sine omega t minus kx, then we'll write the reflected wave as a reflected sine omega t plus kx plus some phi, let's say. Okay. Now, y incident at x equal to 0, just before x equal to 0, is e naught sine omega t. Okay. Y reflected at x equal to just before 0 will become e reflected sine omega t plus phi. Now, because it is a soft boundary, so there should be no phase inversion. Okay. So therefore, your phi will become 0 over here, and your y net at x 0 minus will become the sum of the two. Okay. Now, if you go by the other equation also, you will come to the same conclusion. If you write your incident wave as E naught sine kx minus omega t, then you have to write your reflected as AR into sine kx plus omega t plus some different phase constant phi prime, let's say. So again, y incident at x tending to 0 minus is E naught sine minus omega t, that is minus A naught sine omega t, and y reflected at x tending to 0 is AR sine omega t plus phi prime. Now again, it's a soft boundary, so these two should be in phase. Okay, so these two should be in phase. So in phase kab hoga? When we take phi prime as phi. So if we write this way, okay, so again your y net at x tending to 0 minus will become minus of E naught plus A reflected sine omega t. Okay, so that is the main thing, that if it is, there is no phase inversion, the amplitudes add up, and if there is phase inversion, then the amplitudes have, the net is the difference of the amplitude. That's like a rule of thumb you can remember. Okay, so people, with this concluding the session here today. Okay, and now we are done with waves along a string. So next lecture we will look at the starting part of sound waves, okay, or longitudinal waves or pressure waves, another way of understanding it. And we'll see that up to the interference and standing waves, it's much the same, but with some different notation. And obviously physically they are different waves, but the concepts are very same. And then of course there are additional concepts like additional phenomena like beats and Doppler's effect, etc., which happen in sound. So again, it'll be easy to follow once we've done the basics. Okay, that's it for today, people. Thanks for attending.